Great. So where were we last time? Last time we had discovered that radiation, and we're going back to Lecture 4 notes because I think I have a little bit left on Lecture 4 notes. We discovered that radiation also behaves like a particle. And it behaves like a particle as exhibited in this photoelectric effect. That is, in order to get an electron out, what we needed to do was to put in a particle of energy. We needed to put in a packet of energy. We needed to put in a quantum of energy. And as long as that quantum of energy, that packet of energy, that particle of energy was larger than the work function, we would get one electron out for every packet we put in. All right? So that's an example of the particle-like nature to radiation, this photoelectric effect. All right, but Einstein also went on to show an even more convincing property of the particle-like nature of radiation, or a photon. And that is that he showed that a photon has momentum, even though a photon does not have mass, or essentially no rest mass. Okay? And of course, momentum is a very particle-like property, right? Momentum, hey, P for momentum is equal to the mass times velocity, right? So if a particle, or if a photon, if radiation has momentum, well, gee, it's acting very much like a particle, right? All right, how did he do this? Well, Einstein took the relativistic equations of motion, which he himself wrote down. And what he showed from that is that a photon had momentum P here, and the momentum of the photon was defined by the frequency of the radiation. That is, that momentum was given by h, again, Planck's constant there, that quantization constant, times the frequency over the speed of light. And since, of course, we know the relationship between the frequency and the wavelength, we can write the momentum of a photon as h over lambda. All right? So if you have radiation of some wavelength lambda, that radiation, those photons, have this momentum h over lambda. This photon momentum, even though photons don't have mass. Okay? And the actual demonstration of this took a few more years, experimentally took a few more years. And it was demonstrated first in something called the Compton effect, which was the interaction of an X-ray photon with some matter, and you could see it transfer momentum. And I got to show you here this website from the University of Colorado again. And here, this is just a video of a photon gun here, shooting photons. And here's this enemy atom coming at you. And you're shooting these photons, and sure enough, you can repel that atom, make it go the other direction because of the photon of the because of the momentum of the photon. But of course, if you lower the power and you're not really good with your fingers here, you can get clobbered, right? So here now I'm going to try this again. This is almost too easy. Okay, so now I lower the power so that the rate of the photons are much slower, and I'm going to be able to turn this guy around. No problem. There we go. Repelled it right off. Okay. So it really is the case that, let me see if I can get this guy here. I got clobbered. Okay, well, you'll be better at that game than I am. But it was it's just that phenomena, what I'm showing you here, that led to the experimental feat of atom trapping. You know, trapping an atom in space. And how did they do that? Well, what they did is they took some unsuspecting atom, and they came in with some photons, laser beam, high-power laser beam, directed in this way, and of course that pushed the atoms, that pushed this atom down. But now if you come in with a laser beam in that direction, well, the photon momentum is going to push the atom up, so now you've constrained it in this dimension, and you do it. You send another laser beam this way and another one this way, and now you've constrained it in this dimension. And then you send a laser beam in this way and a laser beam in that way, and constrained it in the third dimension. Hey, you've trapped an atom in space, all right, via photon momentum. And this is what Steve Chu and Stanford and Bill Phillips at NIST did in the middle 1990s, and received a Nobel Prize for this atom trapping here in 1997. No, 1997, sorry. Okay. Photon has momentum. And the reason this is so important, or the reason this experiment was also so important, is because it is the first step in producing a Bose-Einstein condensate. A Bose-Einstein condensate is where you take an atom, which is a boson actually, and you cool it down to such low temperatures that they condense, that these atoms condense. So you've got to cool it down, very much so. You have to get to the microkelvin range. And the first step in cooling an atom down is this atom trapping, this laser atom trapping. Okay? And this will get you down to Kelvin or a little bit lower or so. And of course, what I mean by lowering the temperature is that, you know, I've slowed this atom down, right? The temperature of the gas is related to how fast this atom's moving. If I slow it down, I'm cooling the gas. Right? So this here is that first step in getting the atoms to condense. It's the first step in cooling the gas down. Then there are many other steps. And actually, the Bose-Einstein condensate, one of the individuals who accomplished that feat is right here in the physics department, one of my colleagues, Wolfgang Ketterle. Many of you will get to meet Wolfgang Ketterle. In fact, he might even be teaching a section of 801. Is that right? Pardon? Recitation. Okay. All right. Great. All right. Maybe he'll tell you some more about it if he hasn't already. Okay? All right. So photons have momentum. So now, what have we seen? Well, what we've seen is that radiation exhibits both the wave-like behavior and this particle-like behavior. And just in general, experiments where the radiation produces a change in matter, like the photoelectric effect, that's a change in matter, right? An electron gets ripped off of the material. Experiments in which a change in the matter is affected, in that case, usually the radiation exhibits particle-like behavior. Experiments in which the radiation interaction results in a change in the spatial distribution of the radiation, well, in that case, then radiation exhibits its wave-like behavior. And so, you know, it's not really a proper question or an appropriate question to ask whether light is a particle or is it a wave. The appropriate question is to ask whether light behaves like a particle or behaves like a wave, depending on the particular experimental conditions. Now, this kind of wave-particle duality, or the ability of it to behave like a wave or a particle, is not a contradiction. It's just the fundamental nature of light. It might seem like a contradiction to you because your everyday experience doesn't allow you to see that both properties can be there. Your everyday experience says it's a particle or it's a wave, right? But this is a part of nature, of our world, that you don't have the experience with every single day. So it seems strange, but it is the way light works, right? It's like someone asked me, what is the form of a photon? And when you ask that question, that's fine, but you have to realize what you want for an answer is to draw an analogy between that photon and something that you can experience every day. And the bottom line is you can't draw that analogy correctly because that photon is not something that you can relate correctly to your everyday experience. It's a different part of nature. It's just one that you don't see every day, so it seems strange, right? So you have to be willing to accept kind of new rules, new phenomena that are just outside of your everyday experience. They're out there. As you delve into nature more deeply, you'll see that. Okay? Okay. So we've taken care of radiation, the wave-particle duality of light and matter. And now what we've got to do is we've got to talk about matter. And we've got to talk about its wave-like properties and also its particle-like properties. Well, its particle-like properties are certainly something that is within your everyday experience, right? You can understand matter as a particle. What's more difficult to understand is matter behaving like a wave. So, for example, if you had the situation where you have the surface of a nickel crystal, and what I'm showing you right up here are two nickel atoms, just two nickel atoms of this surface here. Right? And the two nickel atoms are spaced about 2 times 10 to the minus 10 meters from each other, given the lattice spacing of a nickel crystal. And now, if I went and I sent electrons into this nickel surface, and again, I'm just showing you two of the atoms. If I came in with electrons are particles. You know, J.J. Thomson showed us that. And eventually the mass of those electrons was determined. But what you might expect is that those electrons would come in and then backscatter from these surface atoms and do so in all directions. So that out here where we have a phosphor screen, and now that screen happens to be curved just so it'll be easier for us to talk about the geometry of this problem here, you might expect naively that these electrons scatter in all directions and everywhere where they hit the screen, hey, the screen lights up. Okay? Well, this is just the experiment that Davison and Germer did in 1927, along with G. Thomson, George Thomson, the son of J.J. Thomson. Actually, G. Thomson did the experiment in a little different way than Davison and Germer. And I'm going to explain the Davison and Germer experiment here. And now what I've done is I've taken my nickel atoms and just made them smaller. And I did so because I need to clean up this diagram a little bit for the geometry that we're going to do. But I've left the lattice spacing accurate here. And what Davison and Germer did is to bring in an electron beam at 54 electron volts. And they looked to see how these electrons scattered back from that surface, all right, onto that screen. And lo and behold, what they found is that those electrons did not scatter isotropically. They did not go in all directions. But there seemed to be a preferred scattering angle here. Right? And one of those scattering angles right here is 50.7 degrees. So this angle right in here, that's the angle from the surface normal to the direction in which this electron scatters. Right? So they observed some scattered intensity, lots of electron flux at this angle here, about 50.7 degrees. And they observed a lot of intensity right at the normal angle, right here. So the electron comes in and scatters right back. And depending on the experimental conditions, they observed some intensity at a very large scattering angle here. All right? What does this look like? Hey, it looks like interference phenomena, right? It looks like the results of the two-slit experiment that we did. There's a very bright spot, very intense spot, right in the center. Then there's a dark spot. Then there's a very intense spot. Then there's a dark spot. Then another intense spot. Hey, looks like interference phenomena. Well, let's see if we can understand that interference phenomena. So here's that same diagram. I just cleaned it up a little bit. And so what we're doing in the experiment is we're bringing in a continuous stream of electrons, and here's my continuous stream of electrons. And I'm only showing you two atoms, but the same thing's happening on a lot of atoms. All right, so what it looks like is that these electrons are coming in, and then each one of these atoms are kind of acting like a point source, reflecting the electrons isotropically as a wave, right? That is, that there's a wave that's emanating out from each one of these atoms, all right? And of course, as time goes on, that propagates out, and then another wave front, another maximum emanates out. And of course, the distance between these two maxima is the wavelength, right? Because this is the maximum wave front. Here's another one. With time, it continues to emanate out. With time, it continues to emanate out as long as we are throwing electrons at that nickel crystal. And it continues to emanate out until it gets to the screen. And then we see some bright, dark, bright spots. Okay? Hey, looks just like the two-slit experiment. And now if we go to analyze this, and again, this is the same drawing. I just cleaned it up a little bit. If you look at this point right here, what do you see? Well, you see the maximum of a wave scattered from atom 1 at the same point in space as the maximum of the wave scattered from atom 2. Hey, constructive interference. Next point here, again, two maxima in the same point in space, constructive interference. Here, two maxima in the same point in space, constructive interference. Everywhere along that line, we have constructive interference. And so if you project out to the screen, you're going to have a bright spot there. You're going to have electrons being scattered right in that angle. Okay? And now we know, we talked about last time, what the condition was for constructive interference. And the condition is that the difference in the distance traveled by the two waves that are constructively interfering. And now I use the letters D instead of R. Okay? But the difference in the distance has to be equal to an integral multiple of the wavelength. And if you analyzed this line here of constructive interference, you'd find it was n equal 1. The difference in the distance traveled was 1 lambda. All right? And over here, you can see a row of constructive interference. And if you analyze this constructive interference, you would find the difference in the distance traveled was 2 lambda. This is our second order diffraction spot, or second order interference feature. And then, of course, we have the 0 order interference feature. Hey, these electrons are behaving like waves, right? It's constructive and destructive interference. Now, what we're going to do is that we're going to analyze the geometry of this setup a little bit more. We didn't do this for the two-slit experiment with light. We could have, but we didn't. We're going to do it here for the electron scattering. It's really the same thing. And we're going to do it just like Davison and Germer did it, because from this analysis, in particular from knowing what the scattering angle is, this is the quantity that Davison and Germer wanted to measure, right? Or we're really interested in this scattering angle, which turns out to be 50.7 degrees for this first order diffraction beam. We're going to use that knowledge to calculate the wavelength of the electrons. That's what we're aiming for here. And we're going to do that because of this known condition, right? For constructive interference, that the difference in the distance traveled by the two waves that gives the constructive interference has to be an integral multiple of the wavelength. All right? That's where we're headed. So now, see this line from atom number 2 to the screen? I called it D2. D2 is the length of that line. It's the distance that the wave has traveled from atom 2 to the screen. D1 is the distance that the wave scattered from atom 1 has traveled to the screen. All right? Now, I'm going to draw a perpendicular right here. All right? I'm going to draw a perpendicular from atom 1 to this line, D2. Here's the right angle. That's really nice, because look at what this leg of the triangle is then. It's D2 minus D1. Hey, that's a quantity that's going to be interesting to us. Okay? All right. Now, what you have to do is you have to convince yourself that this angle right in here in this triangle is equal to this scattering angle, theta. All right? If you're good at geometry, you can see that immediately, or you might have to think about it a little bit, but it is equal to that. Okay? Well, that's good, because now I got a triangle right here, and I know the length of one side. That's the distance, the spacing between the two nickel atoms in the crystal. And I know what theta is, because that's what Davison and Germer measured. It's pretty good. I can use that. I can use this geometry to say that sine theta is equal to the length of the opposite side, d2 minus d1, over the hypotenuse, a. Okay? And now, if this is the condition that has to obtain to have constructive interference, and then this expression comes from the geometry of the problem that I'm solving. So this is the theory. This is the geometry of the problem I'm solving. Well, then n lambda has to be equal to a sine theta. Okay? And therefore, I can rearrange that to get lambda. Lambda is equal to a sine theta divided by n. And now I can use this information here to calculate what lambda is. All right, I know that the scattering angle is 50.7 degrees. I know what n is. It's the first order diffraction feature because it is the most intense spot that's closest to the zero order. The zero order is always going to be normal to your sample, normal to the crystal. All right. So therefore, I can plug some numbers in there, and I get for the wavelength 1.66 times 10 to the minus 10 meters. All right, so this experiment says that if you have electrons that are 54 eV in energy, the wavelength of those electrons is 1.66 times 10 to the minus 10 meters. Okay, so Davison, Germer, and Thomson, hey, not only did they demonstrate the interference phenomena of particles, right? Particles that had mass, but they were able to calculate from that experiment the wavelength, the corresponding wavelength. All right, but now I just want to take a moment as an aside to tell you that this geometry that I illustrated right here is the identical geometry that is used in X-ray diffraction. X-ray diffraction is the interference or the diffraction of X-rays, photons, right? This is electron diffraction. But the geometries are the same. The concepts are the same. But the reason I bring up X-ray diffraction is because it's a very important technique for you in your future, whether you're going to be looking at materials to get the structure of materials, or whether you're going to be doing some kind of biological chemistry, because X-ray diffraction is used to get structures, crystal structures, particularly of proteins. And the reason why you want to know the structure of a protein is because that structure does give you some hints as to what the function of the protein is. Right? And actually, Professor Drennan, who's going to lecture the second half of the course, that's her specialty, is X-ray diffraction of crystal proteins. Okay? And I'm sure she'll tell you much more about that. All right, but in X-ray diffraction, what they do is they use those results not to get the wavelength, but they use those results to get this distance here, A, the distance between the atoms. That's what I mean by getting out the structure. In X-ray diffraction, they're coming in with an X-ray beam, and they know what the wavelength is of their X-ray beam. So they know what lambda is. And then they go and measure what theta is, the scattering angle. Okay? And from those two quantities, lambda and theta, they figure out what A is, the distance between the atoms, and therefore work out the structure of the protein. Okay? So that's how X-ray diffraction is actually used. All right. Well, now I'm going to need the, I think I can turn these back on. Just get this up a little bit. I'm not going to get the screen all the way up because I still want that number actually. Okay. Now, so not only did Davison and Germer and Thomson demonstrate the interference phenomena, but they also got out of all of that. They got a value for the wavelength. And that was very important. And the reason why it was so important is because a few years before, 1924, there was a prediction for what the wavelength of particles ought to be. And that prediction was made by this gentleman, de Broglie. De Broglie, in his PhD thesis, no less, he made a prediction for what the wavelength of particles ought to be. What he did is he took the relativistic equations of motion of Einstein, the same identical equations. He knew of Einstein's work, PhD thesis, right? And he realized that those relativistic equations of motion apply to matter as well as to photons, to radiation. And so he said that if you have, of course, then a photon which has a wavelength lambda, of course, then that momentum of that photon is p. But since those equations also apply to matter, he then said, well, if you have a particle with momentum p, hey, that particle ought to have a wavelength lambda. He turned Einstein's relativistic equations of motion around, right? He said, well, you know, if radiation has a wavelength lambda. It ought to have momentum p. This is what Einstein said. De Broglie said, well then, matter with a momentum p better have a wavelength lambda. Okay? That's de Broglie's wavelength. Isn't that amazing? I think that's amazing. Why didn't Einstein realize this? Or did Einstein realize that? I don't know. But now let's see about this prediction here. What we know is that in the de Broglie experiment that we had electrons of 54 eV. That means that's the kinetic energy. That's 1/2 m times v squared. You can write kinetic energy as p squared over 2m. You can convince yourself of this. And this is useful to know for these kinds of problems. All right, p squared over 2m is the kinetic energy. And therefore, if this is the energy, you can calculate the momentum of those 54 eV electrons. So the momentum is 4.0 times 10 to the minus 24 kilograms meters per second. And now we can use de Broglie's wavelength here. That expression that he had gotten out of Einstein's relativistic equations of motion to solve for lambda. So that's h, 6.626 times 10 to the minus 34 joule seconds over the momentum. And that gives us 1.7 times 10 to the minus 10 meters. Hey, same as the experiment. It predicted exactly what the experimentalist measured for the wavelength of the electron. All right, this was a real coup here for de Broglie and for science. So, what do we have? We have Davison and Germer and George Thomson, who have demonstrated, and in particular George Thomson, who has demonstrated that an electron has wave-like behavior. In contrast, here's George Thomson's father, J.J. Thomson, who has demonstrated that an electron is a particle, has mass, right? And both the son and the father are correct. How often does that happen, right? It's really an amazing story. Okay. All right, so now, I'm going to have to put the lights off here. I'm getting my lights confused. All right, so now we're at the point where we can begin to understand the structure of the atom, right? Because it was this realization that an electron had wave-like properties. It was that realization of those wave-like properties that led this gentleman right here, right, to realize that maybe he had to treat the electrons as a wave, Mr. Schrodinger. It was that realization that led Mr. Schrodinger to write down the Schrodinger equation, the wave equation, the equation of motion for particles like an electron that actually have a wavelength on the order of their environment, okay? And actually, I just realized that I skipped something in your notes that I wanted to talk about. And I apologize for that. We're going to get to the wave equation in a moment. It's very important. But I did want to just talk about for a moment why, if particles have waves, or have wave-like phenomena, then why hadn't this wave-like phenomena been seen before? So what this also should mean with de Broglie is that you and I have a wavelength. Because we got momentum, we got mass times velocity. We also ought to have a wavelength. So, pardon? They take a while to go up, yeah. All right, so let's consider the problem with our wavelength here. Well, let's talk about the wavelength of a baseball. So we have a 5-ounce baseball, right, being pitched by Curt Schilling at 90 miles an hour. All right. And it's being pitched at a very large nickel crystal. So let's think of an experiment of diffraction of baseballs from a large crystal, just like the diffraction of the electrons from that nickel crystal. Well, let's calculate the momentum of that baseball. That momentum is m times v, and 5 ounces, 90 miles per hour. Get all your units right. It's 5.6 kilogram meter per second. All right? And then we're going to use de Broglie's relationship right here to calculate what the wavelength is of that pitched baseball. And when we do that, lambda is equal to h over p. If you put in this m, or you put in this p, put in h, hey, that comes out to be 1.2 times 10 to the minus 34 meters. Okay, pretty small. All right, but what do we know? Well, we know the condition for constructive interference, d2 minus d1, has to be equal to n times lambda, has to be equal to a sine theta. Right? So now, let's calculate what the angle theta ought to be for the first order diffraction feature of baseballs from a nickel crystal. So you have Curt Schilling throwing these baseballs one or another, right, at this nickel crystal. And you're trying to see at what angle you're going to see that first order diffraction feature. Well, we can set this up so that sine theta here is going to be equal to n lambda over a. So n is 1. Lambda is 1.2 times 10 to the minus 34 meters. And then a is 2.15 times 10 to the minus 10 meters. Hey, if you go and evaluate what theta ought to be, it's 3 times 10 to the minus 23 degrees. All right? So that means if I have my huge nickel crystal here, and here's the normal to the sample, well, then that first order diffraction feature here is at about 10 to the minus 23 degrees from the normal. Are you going to be able to resolve that? No, right? You're not going to be able to see the normal reflection, and then no baseballs, and then a very intense beam of baseballs. You're not going to be able to resolve 10 to the minus 23 degrees. So you say, well, okay, if that's the problem, then maybe I can help myself out by changing this A here, right? By changing the distance of my particles that are doing the diffracting, my 2 nickel atoms. Hey, let's change that distance. Let's find some other crystal such that I change that distance to, oh, let's see, how about 7 times 10 to the minus 33 meters, all right? When I do that, and I go and calculate what theta ought to be, that first order diffraction feature, well, that comes out to about 1 degree. So, if I were pitching baseballs at the normal angle, and I was looking to see if I had a maximum of baseballs 1 degree from that normal angle, 1 degree, could I resolve that? Maybe. Maybe you could get an experiment like that. Set it up. Maybe. But the problem is right here. Right? The problem is in this A, the distance between the atoms that are the distance between the atoms in the nickel crystal that are going to reflect these baseballs. This distance is 7 times 10 to the minus 33 meters. How big was the diameter of a nucleus? What? Negative 10? How about another number? Negative 11? How about another number? 14. 10 to the minus 14 meters. That's a good number to know. What am I looking at here? I'm looking at a distance between the atoms of 10 to the minus 33 meters. Hey, we're 20 orders of magnitude smaller than the size of the nucleus. Do we have a crystal to diffract baseballs off of where the atoms are 10 to the minus 33 meters apart? Okay, we don't. And that's why wave-like phenomena on macroscopic particles has not been observed. Because our wavelengths, your wavelength, my wavelength, baseball wavelengths, these wavelengths are way too small. They're way too small because the mass is way too large. And so there is no way in the macroscopic world that we're going to see any effects, any wave-like behavior from macroscopic objects. Our wavelengths are too small. We've no way to see that wave-like behavior. You're going to need slits, or you're going to need atoms that are about 10 to the minus 33 meters from each other. And that's just not practical. Okay? So for macroscopic objects, for you and me, hey, our wavelengths don't mean anything. They are of no consequence in the observation of what we see around us, right? However, they have lots of consequences for particles, such as an electron, whose environment is on the scale of their wavelength. So I'm saying here, in this case for the electron, where the wavelength is 10 to the minus 10 meters, hey, that is a wavelength that's on the order of the size of the electron's environment in an atom. That's 10 to the minus 10 meters. In those cases, when that wavelength is about the size of the environment, then the wave-like properties matter. They matter. You see the interference phenomena. You see those effects of those wave-like properties. And it is just that realization that led Schrodinger here, who's now washed out, right, to write down the wave equation of motion. And that's an equation of motion for particles whose wavelength is on the order of the size of their environment. And you have to use that equation of motion to understand how that electron, so to speak, moves. You can't use F equal ma. And that's where we will pick up next Wednesday.